In the fourth mini lecture of the aircraft response to control movement, we will study the reduced order modeling for the short period pitching oscillation and the phugoid mode. So regarding the reduced order modeling for the SPPO or the phugoid, we actually already have some idea in the previous lecture. And so in this lecture, we will study it in another way. In the previous lecture, all the quantities UV, UW, Q, and theta are considered in this big matrix, right? And we have the exact solution. By solving this state space form equation, we can have the exact solution, and we see the solution, the transfer function, and also the diagram, how it evolves. Okay, so for reduced order modeling, we don't want to solve the complete equation, but in a reduced way. So we want to eliminate some items or quantities and make it easier to solve. So that's the idea for the reduced order modeling. Okay, so then we have this question: is there a simplified method by neglecting the unimportant variables? And we may notice small u is a very small fraction of the true airspeed, and theta, that's a pitching angle, can usually be ignored if we use wind axis for the short period pitching oscillation. And alpha, angle of attack, does not vary by more than about 2 degrees in the response, especially for short period pitching oscillation. So and for short period pitching oscillation, the angle of attack change is also very small. So under these assumptions or simplification criteria, and we can remove the quantity u and theta. So eventually we only have two equations. Okay, so if we rewrite it, it's like this way. So from four equations, now we reduce the governing equation to two equations. So this is what we have. And we can do some further simplifications. As in the beginning, we talked about the control-free analysis, which means that delta E is a variable, it changes, and we need to consider the input of delta E. But now we are looking at the stick fixed stability. Okay, so then the very right hand term is eliminated. Now I pasted the simplified or reduced order equations, governing equations in here, and we can rewrite it in this way in a matrix form. X dot equals AX, and this is in a state space form. So according to the Laplace transformation, that's what we need to do. So we carry out the Laplace transformation for the state space form. This procedure is exactly when we discuss about the complete form, right, in a previous lecture. Okay, so we do Laplace transformation of the state space form, and then we have S times X bar S equals AX bar S. So this is a transformed governing equation. And so we move the right hand turn to the left hand. So we have the coefficient matrix Si minus A. And then we want to calculate the determinant of that matrix. So we write the Si minus A here, and we want to make it the determinant being 0. So we can do some calculation. Okay, and you can see we have a quadratic equation and about S, and then this is actually what we want, and this is for the short period pitching oscillation. And from here, if we do some analogy with the simple harmonic oscillation, and we can have 2 times cos times omega n equals minus mq minus zw, and also we have omega n. And actually we can make it even simpler, more do some further simplification because ZW is always small, so it's becoming negligible, and we can remove that term ZW from 2 cosine omega n. And also MQ times ZQ and for omega n is also very small, so potentially we can neglect that one. And for the second part, MW times ZQ, and we know ZQ usually has a magnitude of true airspeed. And don't worry about here, and later on we will see an example. And so we just, not for now, we just accept it as a conclusion. And MW times ZQ then can be approximated by MW divided by IY times V. And eventually, we have MW times ZQ equals M alpha divided by IY. That's moment of inertia. Okay. So now we have our simplified solution. Omega n equals this part, and you can see that's the damping ratio can be approximated by this relation. So this is for the reduced order model for stick fixed short period pitching oscillation. And you can see the idea is exactly the similar as what we've done before. So we first start with the Laplace transformation and then get the coefficient matrix, make it determinant being 0. Then we have the damping ratio and natural frequency. We've discussed the reduced order model for the short period pitching oscillation. Now let's start looking at the reduced order model for the Fugit mode. And again, we have these 4 governing equations in here. And in practice, usually xq is 0. So potentially we can replace xq by 0. And also for the Fugit mode, the vertical acceleration is 0, and also the acceleration of the pitching rate is also 0, and so these 3 terms can be replaced by zeros. And potentially, and let's see about x theta and what can we do about the x theta. So for the longitudinal analysis, the longitudinal force equals minus mg tan theta. So y tan theta actually should be sine theta because theta is a small angle and then can be approximated by theta. And then we can do the derivative, small x theta equals big X theta divided by m equals minus g. So later on, x theta can be replaced by minus g. Okay, so now, because again, we are considering the stick fixed control, so the second part in the right-hand side can be eliminated because it's being 0, delta E is 0. Okay, so now what we are doing is extract equation number 2 and equation number 3 out. And so we have this equation. So if we rewrite equation 2 and 3 into this form, so W can be expressed as a function of U, Q can be expressed as a function of U again. Okay, so you may wonder why we write it this way. You will know later. And now what we do is we rewrite equation 4 and 1 together. So the equation 1 is about the axial acceleration, and the equation 4 is about the theta. Actually, theta, the rate of theta change. Yeah. Okay. So now what we do is replace, just plug in the result from equation 2 and 3 into equation 1 and 4. So you may imagine it already becomes very complicated equation. Now let's move further. So we already put them in. So the equation 1 and 4 can be written as this way. So you see it's becoming more complicated, but don't worry, we will simplify them. So this is what we have. And now we want to write it down as matrix form. And the left-hand side is the acceleration, and the right-hand side is the original variable. And actually this, we can see this as a state space form, right? And then what we do is similar as the analysis for the short period pitching oscillation, we can do the Laplace transformation. I'm just skip that part because exactly the same. And we, after Laplace transformation, we will look at the determinant of the coefficient matrix, that's Si minus A. And in here, I'm writing down here, and the determinant should be 0. And then we can similarly get a quadratic equation. And if we compare again with the simple harmonic equation, we can find its natural frequency and the damping ratio, right? Okay. So now let's see some numbers before we do the simplification. For the Corsair aircraft, fighter jet, and we've seen this aircraft earlier, and if it's on the wing axis, the coefficient matrix has the following numbers, and you can see there are a few zeros and also a few quite small numbers, especially mu. And I'm copying the expression from the previous slide, 2 cos times omega equals this. And now let's see how can we simplify it, because mu is very, very small, and especially the right hand side, if we do the calculation, we'll find they are very small. So 2 cos times omega equals can be approximated by minus xu, and then minus xu is actually minus big xu divided by m. So this is what we have. Okay. So we can do something further, because Cxu, that's the coefficient, aerodynamic derivative coefficient, equals minus 2cd. That's the drag coefficient. And we have xu equals minus 2cd times half rho vs, and eventually become minus cd rho vs. And mg equals cl half rho v squared times s. So this is gravity. And then we have 2 times twice cos omega equals 2g cd divided by vcl. So this is more straightforward of the simplifications. Okay, and if we move to the square of the natural frequency, and it becomes this, and because if we do some calculation by plugging these numbers as an example, and it will become minus gzu divided by zq. And zq, we can move up. You can see that zq is 317.5. It's usually the true air speed. So we can replace zq by v. So eventually, omega squared equals minus g and zu divided by mv. Okay, and for zu we can do something similar as xu, and zu can be approximated by minus 2cl times half rho vs. Okay, so eventually omega squared can be approximated by 2g squared divided by v squared. So in here, we can have omega equals square root of 2 times g divided by v. And since we already know the natural frequency, and then we can find the damping ratio. So this is for the reduced order model for the fuel-going mode. And you can see it's the principle is actually quite similar as the short period pitching oscillation, how we do the model, but there are different criteria for the simplifications or to reduce order. Okay, and for the reduced order modeling for the fuel-going mode, and here is a comparison between the reduced order result and the full order result. And you can see the for both models, the damping ratio and also the especially the period or the frequency looks quite similar. Just after I think after about 4 seconds, that's one period, the disparity becomes larger, especially for Q, becomes much larger than the other two. But at the beginning, they are very close, especially the estimation of the period or frequency are quite close. So this is what we've done for the reduced order modeling for the SPPO and the Fugoi mode.